Today we are extremely honored to have Tracy Slatyer visiting us from MIT. Tracy did her undergraduate work with honors in theoretical physics at the Australian National University, ANU, and her PhD in physics at Harvard, where she worked with Doug Finkbeiner. Tracy was a postdoc at the Institute for Advanced Study, as was I later, and joined the MIT physics department as a junior faculty member in 2013, where she was recently promoted to associate professor in 2018 and received tenure in 2019, after which I had the pleasure of overlapping with Tracy briefly at the Institute for Advanced Study, where she was visiting faculty, and I was a postdoc. Tracy has won all sorts of awards, and if I listed all of them, we would not have time for the colloquium, but suffice to say that these are awards for her fascinating work in theoretical physics, as well as her work in teaching and mentoring and contributions to the field broadly. Two brief highlights include the Bruno Rossi Prize of the American Astronomical Society, and most recently in 2021, the New Horizons in Physics Prize for major contributions to particle astrophysics from models of dark matter to the discovery of the Fermi bubbles, one of the many, many discoveries for which Tracy is well known. So I am delighted to welcome Tracy today to tell us about bound states in heavy dark sectors from WIMPonium to Squeezeout. And with that, I will turn it over to Tracy.
Well, thank you very much for the very kind introduction, Susan, and for the invitation to all of you. I'm very happy to be back here. It's been a few years, so it's really nice to be back at Stanford in person. So today I want to tell you about work that I and my collaborators have done on the general topic of what if dark matter could form bound states? What would some observational consequences of that look like? So I first want to begin, since I know not everyone here spends all their time thinking about dark matter, just talking about the puzzle of dark matter, what we think we know about it, what we know we don't know about it, and what some of the possibilities could be for solutions to those problems. Then I want to go on and say a little bit about what might happen if dark matter is not the only new particle that we're looking at. What would happen if dark matter is embedded in a new dark sector and could feel its own dark forces? What if dark matter has non-negligible interactions through the forces that we already know about? And in particular, what if those forces could support bound states? And then I want to give you two specific examples of things that could happen in those kinds of models. So one, I'll take the example of WIMPonium, where dark matter interacts through the weak gauge bosons of the standard model, and I can say a bit about how that would affect gamma ray signals from such models. And then I want to give you a different example where instead, so for the first case, the analogy is like the hydrogen atom or positronium. In the second case, the analogy is more like the strongly interacting sector of the standard model, like QCD. And I'll argue that in that case, there's a natural regime for dark matter that's very heavy, much above the weak scale, due to modifications to the cosmological history. Okay, so I do welcome questions as we go. Susan is going to track the Zoom chat for me and let me know if there are questions from Zoom. People in the room, just feel free to put up your hands and ask a question if you have any questions as I go along, and I understand there'll also be some time for questions at the end. Okay, so let's begin with the big question, the million or billion dollar question, which is what is dark matter? So what do we know about dark matter? So the definitional property of dark matter is that it's a component of the universe that doesn't scatter, emit, or absorb light at a level that we have yet detected. So really, that's the dark part of the name, but really transparent matter might be a better name. But it does have mass and hence gravity, and that's the matter part of the name. So dark matter is really just a placeholder for some component of the universe that appears to exist, that gravitates, but if it interacts with light, it does so at a level that we haven't detected yet. And Susan, can you just check, can people on Zoom hear me okay and see okay? Okay, very good. So we know a few things about this dark matter besides its existence. We have pretty good evidence that it's about 84% of all the matter in the universe by mass. And that precision measurement comes from observations of the cosmic microwave background radiation, which is the earliest direct light that we can see from the early universe. It was emitted when the universe was a few 100,000 years old, and where we think we understand the physics very well. And we can match the observations beautifully, but only if we include an extra component like this dark matter component. Okay, so we know something about how much. We also know something about where the dark matter is. We believe that the dark matter, that those little fluctuations in the cosmic microwave background later grow into large-scale structures that form the scaffolding for the galaxies that we see in our universe. So this figure over on this side of my screen, I think you can see the cursor, is showing the result of simulations of how structure grows over our universe's history by my colleagues in the Illustris collaboration. So this is going from early times at the bottom of the page to late times at the top of the page, and the left panel is showing the predicted simulated density of dark matter, whereas the right panel is showing the density of visible matter. So the picture here is that behind every galaxy that we see, behind the gas clouds that we see with our telescopes, there is an underlying much more massive scaffolding of dark matter. And it was the growth of that dark matter structure that formed the seeds for galaxies in the first place when the ordinary visible gas that we can see was attracted into regions of high dark matter density by its gravitational effect. So the universe that we see, dark matter is the backing, we think. Now, this is a bit of an ahistorical presentation because I can say this to you today, but the way that we got our first clues to dark matter in the first place was by just looking at how stars and gas clouds and other traces behaved around galaxies, and noting that if you looked at how objects orbiting around gas clouds were moving, they appeared to be moving much faster at large distances from the center of the galaxy than you would naively expect. And from that, back in the 1970s, Vera Rubin and her collaborators inferred that most galaxies were surrounded by large halos of dark matter. And now, we understand why that should be so. Galaxies are surrounded by halos of dark matter because halos of dark matter are the nurseries where galaxies are born. So we know something about where the dark matter is, about how much of it there is. And those are all positive statements, but we also have an important negative statement about the properties of dark matter, that if it has non-gravitational interactions with other particles, those interactions must be weak or absent, because we have a large experimental program that's been looking for non-gravitational interactions of dark matter with other particles for some decades, and so far we have not found any confirmed detection. All right, so based on that, what can we say about the properties of this dark matter? So this is enough to tell us that we cannot explain these properties well by any physics that we currently understand. So we want something that is stable, that is electrically neutral. The best candidate particle in the standard model is neutrinos, but neutrinos are too light and too fast moving to make that cosmic web that I showed you. So the galaxies would look very different and their history would look very different in a universe where neutrinos were all the dark matter. Now, this is not, now that there are some candidates for dark matter that are mostly within the standard model, like primordial black holes left over from the very early universe, but it's still true that in order to make those things in the first place, we would need some physics that we currently understand. So this is a gap in our knowledge. Some of the things that we don't know about dark matter, we don't know what it's made from. We don't know if we're looking at like one kind of new particle or many kinds of new particle, or something that we wouldn't normally consider a particle at all, like the aforementioned black holes left over from the universe's very early history. If it interacts with other particles through forces other than gravity, we don't know that yet, although we have some reason to hope that there might be such interactions. We know that the dark matter has to be pretty stable because we have evidence that it was around when the universe was a few 100,000 years old and is still around today. So for that, it has to have a lifetime somewhat longer than the age of the universe. If it decays into anything visible, we can actually show it has to have a lifetime 8 or 9 orders of magnitude longer than the age of the universe. But it could still be unstable, just with a long lifetime. Why the dark matter abundance is what it is. Where is this? Does this 84% number come from? We have a lot of hypotheses for this, but we don't know the answer. And is it connected to other deep problems in particle physics? Would be nice if it was, but this also remains an open question. So on that last front, this is a slide that my colleague Tim Tate made as part of the SNOMAS community planning process that the particle physics community went through almost 10 years ago. We're currently in the second iteration, we're currently in the present iteration of this process at the moment. And so maybe in a few months, I will have another nice summary figure like this to show you. But for the moment, there are just a few things that I want you to take away from this image. So everything within these red regions is a class of scenarios for what dark matter could be. So a gap like this is a great invitation to theoretical particle physicists to think about what could possibly solve the problem. And in the case of dark matter, we have many, many ideas for what could possibly solve this problem. Everything outside the red regions is a class of larger puzzles in particle physics that could be connected to what the dark matter is. So dark matter could be connected to new symmetries of our universe. It could be connected to extra dimensions. It could be connected to puzzles related to the Higgs sector or the strongly interacting sector of the Standard Model or the neutrino sector. On this side of the plot, you have the dark matter could even experience its own forces that we don't know about because the particles we know about don't feel it in the same way the dark matter does not feel electromagnetism. So we have lots of ideas for what dark matter could be. If we could figure out what it was, it could potentially, as well as solving the dark matter puzzle, be a key to unlock other aspects of theoretical physics. But unfortunately, the corollary of we have many ideas that could explain what we've seen is that none of these ideas with the results we have at the moment are very experimentally distinguishable because from the perspective of their gravitational effects, they all predict matter that gravitates and has weak interactions. So this has prompted a large experimental program to try to find any indications of non-gravitational interactions between dark matter particles with each other or with the visible particles. And the classic separation of these searches is into indirect detection, direct detection, and collider physics, although there are some limitations to this classification and some sort of extra branches on this plot in the present day. But the basic idea is that you can separate dark matter searches into one, cases where interactions of the dark matter particles out in space produce visible particles that we can look for. This could be by this kind of annihilation. So here chi indicates the dark matter, SM indicates Standard Model visible particles, the blue circle indicates the mystery interaction that we would like to probe experimentally. So the idea of indirect detection is that if out in space, dark matter particles crash into each other, that could produce visible particles that we can look for. The idea of direct detection is that dark matter particles could bounce off Standard Model particles, causing them to recoil. We can search for those recoils and use them to learn about the dark matter fluid. Or in collider searches, we can reverse the diagram, and as we smash Standard Model particles together, potentially get dark matter particles out. And there are variations on these scenarios. For sufficiently light dark matter, it may be able to oscillate back and forth into photons in particular environments. So then you get oscillation searches. You can have accelerator searches that are not collider searches, searching for dark matter or particles closely related to it. But this is still a reasonable framework in which to think about these searches. And the mnemonic that I like for this is break it, shake it, make it. You can convert the dark matter into visible particles, look at the effects of dark matter just bouncing off visible particles, or try to make the dark matter in colliders. So again, this is a large, multifaceted experimental program, lots of ways to look for dark matter. So far, we don't have any confirmed detections. But what I want to do in today's talk is not talk so much about direct searches for dark matter, but about theoretical scenarios for what dark matter would be and how it might behave and how it might change these experimental signatures. And in particular, I want to think about the possibility that maybe dark matter, either through its own new force or through the forces we already know about, can form bound states. So why might we think about this? Well, in the Standard Model that we know and love, bound states are pretty ubiquitous. We have, we're all made up of atoms, and the atoms have nuclei at their cores. So stable bound states are the building blocks of most of the physics that we see. You can also have unstable bound states like mesons, or particle-antiparticle bound states like positronium, which can decay away. These are not as ubiquitous in our present day life because they're unstable. But of course we can create them, and we can look for their signatures in a range of experiments. So we might ask some questions about under what circumstances could dark matter form bound states, and if it could form bound states, what would be some experimental signatures of that? So I want to now I'm not going to try to persuade you today that dark matter absolutely must form bound states. It's quite possible that it doesn't, all right? We're just going to work through a few examples of if it could, how would we know, what would we look for, how would it change the signatures? Okay, and that's my little cartoon of maybe you can have an unstable bound state that decays into visible particles. All right, so let's just first say a little bit about under what circumstances could you get a bound state? What kind of features would a dark sector have to have such that you would expect bound states to be ubiquitous? So if we think about atoms, what do we need to make atoms? Well, we need we have the electromagnetic force supports bound states of atoms. But more generally, if you have any attractive potential between two particles, and it's sufficiently strong or has a sufficiently long range, it will generically support some bound states. So what does long range mean here? It means that the range of the interaction should be larger than the Bohr radius of the bound state. If I try to support a bound state, and you can, if you've done quantum mechanics classes where you looked at the finite square well and number of bound states in the square well, you would find that the number of bound states depended on the width of the square well and how deep it is. So, more generally, the number of bound states that you have depends on the strength of the potential and what its range is. Now, the Bohr radius of the bound state in the hydrogen atom case, we know that if there's some coupling in the describing the strength of the potential, we'll call that alpha. And the reduced mass of the system, I'll call it mu here, then the Bohr radius is like 1 over alpha times mu. So what we would like it to be true is that the range to have bound states in our system is that the range of the force is longer than that Bohr radius. So the force like doesn't die out before you can finish producing the bound state. So if we think about potentials that are mediated by some kind of massive force carrier, some kind of massive force particle, they have a characteristic length scale that is 1 over the mass of the particle. So if we want that range to be longer than the inverse Bohr radius, that means that the mass associated with the force carrier should be less than the inverse Bohr radius, which is alpha times mu. So long as given dark matter coupled to some other particles, which could be standard model particles or non-standard model particles that mediate a force, if the force is attractive and the mass of the mediator is related to the mass of the interacting particles, so maybe the dark matter in this case, by this relationship, then you will pretty generically expect to have some bound states in the system. Now, if you've got a massless force carrier, this really could be like the hydrogen atom, where you actually have an infinite tower of bound states. In general, as you have a force carrier with a finite mass, that'll give you a shorter range potential, and you'll end up with a finite number of bound states. And as you continue dialing up the mass of the force carrier, you will eventually run out. So bound states are going to be generic features of dark sectors that have either pretty strong interactions when this alpha is of order 1, all you need is the force carrier to be of comparable mass to the dark matter, or where there are force carriers that the dark matter can interact with, which are much lighter than the dark matter itself. And if these things happen, you will pretty frequently be able to get bound states. Okay, so then we might split these scenarios, these possibilities into 2 scenarios. One is where the force carrier is something that we know about already. So there's the dark matter and there's the standard model, and the dark matter has some interactions with particles in the standard model that mediate an interaction between them. So, one possible candidate, the classic candidate, is that dark matter is a weakly interacting massive particle, or a WIMP, where the classic version of this scenario is the dark matter interacts with the weak gauge boson. So with the W and Z boson, or with the Higgs boson. Now, the W and Z and Higgs bosons are all around 100 GeV in mass. And we don't usually think of the weak interaction as being a long-range interaction, right? We normally think of this as being a very short-range interaction compared to electromagnetism. But is it long-range enough to support a bound state? Well, the weak coupling strength, alpha weak, is about 1 over 30. It's a factor of a few larger than the fine structure constant, which is 1 over 137. So what our criterion suggests is that if the particles being bound together are heavier than about 100 GeV divided by 1 over 30, then we'll have bound states in our system, supported by the W and Z bosons. So that suggests that we need the bound state constituents to have masses around 3 TeV or heavier. So as soon as you have dark matter heavier than a few TeV, if it interacts with the W and Z bosons, that can give rise to effective long-range forces between the dark matter particle and 2 bound states. So that's what I'm going to talk. So that scenario points that if you want bound states supported by the W and Z, you want heavy, weakly interacting massive particles. This is a class of scenarios that has been thought about a lot. So I'm going to talk about that as one of my examples of this case of WIMPonium. The second, and there will be some general, so we'll look at some specific examples in that case, and this will teach us some general lessons about how dark matter bound states could behave. The second scenario is broader. It says, okay, so forget about the standard model force carriers. What if the dark matter inhabited its own dark sector, felt forces that we don't necessarily know about? Now the dark matter and the dark force carrier could have a wide range of masses, and we could think about some more general darkonium, which was a bound state comprised of dark matter or related particles bound together by this dark potential. In this case, your parameter space is way more wide open, but you still know that either you need a hierarchy in mass between the force carrier and the dark matter in a weakly interacting dark sector, or you need it to be a strongly interacting dark sector. My second example that I'll tell you about is a case of a strongly interacting dark sector where the presence of those strong interactions changes the cosmological history quite a bit and opens up some new parameter space at high masses. All right, so that's my introduction. Now I want to tell you about the examples. So I guess I'll just stop before I go into this and ask if there are any questions at this stage. Yep.
So when you define a dark vector, are you necessarily defining like a vector mediator as part of the dark vector or as like something between?
No, good. Okay, so the question was, when I talk about dark sectors, am I imagining like the dark matter, which talks to a dark photon, which is some kind of vector mediator? So not necessarily, although that's certainly a kind of classic dark sector where this could be relevant. In general, the kinds of force carriers that mediate long-range interactions are vectors and scalars. Both will give you like a Yukawa potential. In the scalar case, it's always attractive. In the vector case, it can be attractive or repulsive. That force carrier might or might not be a mediator to the standard model. So you can have, so this would include setups where you've got dark matter and it's got a dark Higgs and a dark vector, and one of those couples to the standard model. That could certainly fit this bill if the dark vector is light enough or strongly enough coupled to the standard model. But it doesn't have to be like that. You could also get behavior like this in cases where the dark sector is totally secluded and doesn't have any direct coupling to the standard model at all. And there could be, and there are some interesting signatures of dark interactions in that case as well, in addition to this bound state case, just like the scatterings between dark matter particles can have observable signatures. So I'm trying to keep things somewhat general here. I'll show you, two specific examples in this, but yes, this can capture dark matter coupled to a much lighter dark vector. With weak coupling, that's certainly one possibility. And yeah, and I mean, I can talk more if you're interested in like what the bound state signals would look like specifically in that case.
You do have one.
Yeah.
The chat will
Okay, ask the question later. Okay, very no worries then. All right, so let's jump into the first example, which I said. So I want to talk here about dark matter that talks to the W and Z bosons. So the classic weakly interacting massive particle. So this is a weakly coupled system, and I'm going to be interested in unstable bound states. So the analogy in the standard model that I want to use here is positronium. So positronium is a bound state of an electron and its antiparticle. And so these sort of diagrams here are showing schematically, we've got an electron and a positron, they're exchanging photons back and forward between each other, and that's what binds them together. So if we ask, okay, I'm given a free electron and positron, how do I get them into a bound state in the first place? So just by energy and momentum conservation, if I send an electron positron in and I get a bound state out, there has to be some other particle in the final state to carry off the other energy and momentum, and that's typically a photon. So the way that we form these things is by radiative capture, where the two particles come in, a photon is radiated off the electron or positron line, for those of you who have looked at Feynman diagrams, and you end up with a bound state and a photon being radiated. And we can compute the rate of that transition just in the context of quantum mechanics. We can work out the wave functions for the initial electron and positron and the Coulomb potential. It's the same calculation as the hydrogen atom, just with a different reduced mass. And then we can use perturbation theory to compute transitions between levels of the positronium or transitions between the bound state and the continuum case, just like you would for the hydrogen atom, all right? So those of you who have taken or taught quantum mechanics, this is just the same as the Bohr atom. It's the same as the hydrogen atom. Okay, so when you think about experimental signatures from this, we could look for either the photons produced when the positronium first gets formed, or if it gets formed in an excited state, there'll be extra photons as it transitions down to the ground state. But there's another source of photons, which is this positronium atom is unstable. Eventually, it's going to decay because the electron and positron can annihilate with each other. So this picture down here sort of shows the simplest version of the annihilation. The electron and positron just annihilate within the bound state and make two photons. The number of photons that you get out of this actually depends on the spin configuration of the positronium. If you're in a spin singlet state, you can just go to 2 photons, but if you're in a spin triplet state, there's a theorem that says you can't just go to 2 photons, so you have to have 3. So that's fine. So we have these two kinds of signals: annihilation photons from the decay of the bound state and transition photons from the formation of the bound state. And we can look for all of those. Now, it turns out that if we just think about if we had a lot of positrons out there in space and we were trying to figure out if they existed, you might ask, okay, what is the dominant process for these positrons? Do they form bound states with electrons and then those bound states decay? Or is it more common just for a positron to just smash into an electron and immediately annihilate without going through an intermediate bound state? It turns out that at low velocities for positronium, the bound state for positrons and electrons, the bound state process is actually about 3 times as important as the direct annihilation process. So if you were to try to calculate signals from positron-electron annihilation without taking this bound state into account, you will get the wrong answer by a factor of 4. So, all right, so we should understand if we want it, so if these were dark matter particles forming bound states and annihilating out there in the galaxy somewhere, we would like to look for the signal from those particles. We'd like to understand under what circumstances are they like positronium? Under what circumstances do we have to worry about them finding a bound state and then decaying? And are there interesting signatures either from that or from the analog of this process from whatever gets emitted when the bound states are first formed? Okay, so this is the analogy that I would like you to keep in mind. Okay, so what is the class of dark matter models that we're going to think about in this case? Now I'm going to tell you a model scenario. And again, this is one example. We'll learn some general lessons from it that can be applied more broadly. So I argued earlier that if I want to go through the W and Z bosons, my dark matter mass had better be about 3 TeV or heavier. Yep. Yeah.
Analytically governed, that factor of 3 is a simple percentage.
It is not. I actually deleted from this slide the equations, but it is not super simple to say. The calculus. So the scaling with the coupling is identical in both cases. The scaling with the velocity is the same. They both go like 1 over the relative velocity of the particles. The scaling with the electron mass is the same for both. That's just dimensional analysis. They both go like 1 over me squared. So the factor of 3 is entirely, the positronium calculation has a bunch of like factors of 2 and pi and 3 out the front. And it also has a somewhat interesting factor, which we'll see come up later, which is e to the -4 in the positronium case. And we'll see how that behaves in the more general case. Where those factors come from is the way you do this calculation is basically an overlap integral between the wave function of the scattering state, the wave function of the bound state, and then with like a dipole capture operator sandwiched in between them. And the overlap integral between those wave functions gives rise to these non-trivial numerical factors. In the case of positronium, that happens to be a factor of 3 relative to the annihilation case. But one of the things that I'll show you later is that we can actually do this analytically for more complicated dark sectors. And that factor in general turns out to be e to the -4 times a factor that depends on the representation. So as you change the representation, that factor can skew around wildly. And so dark sectors that are not very different can end up having like very different ratios of the bound state production to the annihilation.
I was going to say, as you generalize to like different fermionium theory, you say the factor changes also? Like,
yes.
Okay.
So okay, if you're in the limit, there is a limit that is just like positronium, where it's like the only things that matter are you have dark matter and you have a light vector that is approximately massless compared to everything else. In that case, the math is literally just positronium in the limit where that vector mass goes to 0. And so then in that case, like there's no difference. It's just positronium. But as soon as you start thinking about like non-abelian engaged sectors, so we'll use the example of SU2 here. But as soon as you start thinking about cases with multiple force carriers that are relevant, where the dark matter is like not just like charged under some U1, then that number can move around quite a lot. That now, in addition to that, that's the number can move around a lot, even in the limit where the force carriers are massless. As soon as the force carriers have some non-trivial mass, then you can get resonant effects which further change the bound state formation rate relative to the annihilation rate. Sorry? So in our WIMPonium case, which I will show you the results for, we're going to use the W and Z bosons as our force carriers. So there will be mass-dependent effects as well. And in some cases, which we'll see, there are selection rules that just mean there is no bound state formation that is relevant. Like there's a bound state in the spectrum, but getting into it involves like having to emit multiple photons at a time, and it's just super suppressed. So we're going to use the WIMPonium as basically a test case to see some of these effects that occur when you go beyond positronium. But the baseline answer that I'll tell you already is the answer here is pretty model dependent, and we can write down some general statements that allow us to estimate without doing the full calculation whether it's going to matter or not in a given model. But it can skew around wildly depending on what your dark sector model is. Okay. All right, so now having given you a preview of the next 10 minutes, let's go ahead and look at it. Okay, so here is a model. So we're interested, so we want a dark matter model that interacts with W and Z bosons and that has a mass of 3 TeV or heavier. Now, there is actually a very minimal class of dark matter models that satisfies this criterion. It was named minimal dark matter by Cirelli et al. Back in 2005. And the way that you generate these models is you say, all right, let's suppose that you just taken a quantum field theory class and you'd learned that the standard model gauge group is U1 times SU2 cross SU3. And you say, I want dark matter that is charged under the standard model SU2. If you are an undergrad or a grad student who hasn't taken QFT and you're not sure what I mean by that, don't worry about it. I will explain what you need to know for purposes of this. But so then you can say, all right, let's just imagine the dark matter is some new particle that transforms in some representation of the standard model gauge group. And then we can classify the possible of the standard model weak gauge group. And then we can classify the possible representations of SU2. We'll assume that it's just, just in all in one representation. It's not a mixture of two different representations or something like that. What that means in practice is that we can characterize exactly how the dark matter has to interact with the W and Z bosons, and then it has to be part of a multiplet of particles which also interact with the W and Z bosons. And which representation it's in basically tells you how many particles there are in the multiplet. Typically, so what we call the triplet representation, there are 3 particles in the multiplet. Quintuplet representation, there are 5 particles in the multiplet. You can see the pattern from here. And typically what happens, not always, but what typically happens in these cases is that the other particles in the multiplet can have electric charge and the dark matter is the neutral one, which also tends to be the lightest one and hence is stable. And it turns out that in this case, there's only a limited number of possibilities that, that allow you to satisfy the criteria of having a neutral, stable dark matter particle that doesn't violate other constraints. And so 2 of these possibilities, the doublet and triplet representations, show up as the Higgsino and the Wino in supersymmetric theories. So in supersymmetric theories, every particle in the standard model has a counterpart, usually a heavier counterpart. And so the Higgs boson and the W boson both interact through the weak forces. They get fermions that interact in closely related ways, which get called the Higgsino and the Wino. But you don't need a supersymmetric theory for this kind of idea to be true. I mean, you can have dark matter particles that transform you could have dark matter particles that transform in representations of SU2, whether or not they're part of some larger supersymmetric structure. So I'm going to use, so when you think about, okay, these minimal dark matter models, they have one free parameter basically, which is the mass of the new particle. That we can't predict from the SU2 gauge symmetry. The SU2 gauge symmetry tells us about the interactions, but not about how heavy the dark matter is. But we can ask, all right, as we change this adjustable parameter for the dark matter mass, we change how much dark matter we predict in the universe. So we can ask, what mass do you need to get to match the observed amount of dark matter today? And that answer ends up being about 1 TeV for the Higgsino, so bound states aren't very important for it. About 3 TeV for the Wino, so that's great. That's right about where we thought bound states should start to matter. And it's about 14 TeV for the quintuplet. So, okay, so I'm going to use the Wino and the quintuplet as an example of 2 sort of heavy, weakly interacting dark matter particles with mass scales up at the multi-TeV to 10 TeV scale, where we might expect bound states to be important. Okay, well, happy with this? All right, so I will say we wrote a whole paper on the Wino case. The quintuplet case is still in progress, but I'll show you some preliminary results. So first you might ask, right, okay, how are we going to go after these generally? Maybe they're already ruled out. Well, it turns out that if you're starting with 3 TeV dark matter particles, it's really hard to make them at a collider. If you're dealing with a 14 TeV dark matter particle and you need to make a pair of them, that is definitely not going to work, even at the LHC. This upper panel is showing some limits on Wino dark matter from the LHC, and you can test the possibility of Wino-like dark matter particle masses up to a few hundred TeV, but you would need it to be 3 TeV to explain all the dark matter in the universe. It turns out, so I told you, the other ways to look for dark matter, we can look at direct detection. We can look at the particles just bouncing off targets in our experiments. And that would be a great idea, but unfortunately, the predicted signal for these things is very tiny. And go through the details for people who want to see the QFT, but basically it's naturally quite suppressed. And then there are some annoying accidental cancellations, which make it even lower. So basically the direct detection cross-section sits right around the neutrino floor for pretty heavy dark matter masses. And we just haven't gotten down that far, although we may be able to with future experiments. So then the third option that I told you about was indirect detection. Dark matter particles crash together in the universe. And that's the case where this bound state formation and decay might be important as an additional annihilation channel. All right, so that's what we're going to look at the production of bound states of dark matter out in the galaxy and how they would contribute to an indirect detection signal. So here's the analog of the positronium slide, what happens in this WIMPonium case. So first, I said there are these partner particles, these charged particles, these charginos that couple to the dark matter through the W and Z bosons. So those particles are going to be part of any bound state. So this upper figure here is showing like what a Winoonium could look like. The dark matter particles can exchange a W boson which gets you into like a so here for the WINO, I said there are 3 particles. There's the dark matter, which is electrically neutral, which is the chi-naught, and then it has 2 partner particles which carry opposite charge, which I'll call chi plus and chi minus. Okay, these are the charginos. So when we think about, so in the positronium case, we just had an electron and a positron exchanging photons back and forth. But now that's not quite what's going on, because with these particles exchange a W boson, they're going to turn from a chi-naught pair into a chi plus chi minus pair. Good. For the WINO, so there's an irreducible contribution to the mass splitting that just comes from the fact that the charged ones interact with electromagnetic with the photon and the neutral one doesn't. And that makes the charged ones heavier than the neutral one by about 165 MeV for the pure WINO. So it's a very small mass splitting compared to the mass of the particles, which is important actually. If that mass splitting was too large, those heavier particles would decouple and wouldn't participate in this. But in this case, it's a small enough mass splitting that the potential knows about them. For the quintuplet, so for the quintuplet, there are 5 particles in the multiplet. There's like the chi-naught. There's a pair of singly charged particles, chi plus and chi minus, and a pair of doubly charged particles, so chi plus plus and chi minus minus. For the single particles, the mass splitting is the same as for the WINO, and for the doubly charged particles, it's 4 times larger. Just goes like the charge squared. So now, if you're in a supersymmetric theory, then these in general won't be just pure representations. There'll be some, like the mass eigenstates will be some admixture of the various neutralino quantities that are available here. And then you can get extra contributions to the mass splitting, which depend on like the scale of the other particles in the theory. But the sort of minimal prediction, if you really want to say that it's just this is all there is, there's no more complete theory, is at the level of hundreds of MeV. And it's almost independent of the dark matter mass. It basically just depends on the coupling and the mass of the force carriers, W and Z bosons. Good question. Okay, so when we imagine a WINOonium in this case, what we really have is a bound state that is like a superposition of dark matter particles and chargino pairs bound together by exchange of the W and Z bosons, and also by the photon actually, because the chargino component is charged, and so it has a Coulomb potential between those. So that's what the bound state looks like. So again, to get into it, we need to radiate something to conserve energy and momentum. And because there are charged particles involved in this superposition, the thing that you radiate could be a photon. That's often the easiest way to go. If you want to radiate a W or Z boson, you have to have enough binding energy available to actually make an on-shell W or Z boson. That can happen if the dark matter is heavy enough, but it has a higher threshold. It tends to only happen when the dark matter is, so for the WINO, it would require the WINO-like particle to be 300 TeV or heavier. For the quintuplet, it starts to become relevant around the 14 or 15 TeV scale. So we may have to worry about radiation of Ws and Zs there. We're going to start by just thinking about the photon radiation. Now, the calculation is a bit more complicated in this case, just because these bound states are bound together by exchange of charged particles as well as neutral particles. That means that we can effectively radiate the photon off the charged W bosons as well as off the chi plus and chi minus. But this is kind of a technical point. The physics is still the same. To conserve energy and momentum, if I want to make the bound state, I have to radiate something else. And we could look for those transition photons or the effect of those transition Ws and Zs, as well as the eventual decay of the bound state. So these kinds of features where you've got multiple force carriers, you've got partner particles as well as the dark matter that can be bound together in the bound state, and you can have like new terms like this in the calculation. That can also appear with new dark forces, with any case where you've got a dark sector that's got multiple force carriers that can potentially be relevant. Okay, so this is the kind of bound state that we're going to think about. So now all right, so we've said this bound state is really not just a dark matter bound state, it's a superposition of dark matter particles and other particles in the dark sector. Now, furthermore, there's an important selection rule on what kinds of bound states you can form here. So the Pauli exclusion principle tells us that the 2 identical fermions can't occupy the same state, and if I have 2 identical fermions on my wave function, so like 2 we know dark matter particles in this case, chi naught and chi naught, they have to be in an anti-symmetric state. So if the dark matter is a fermion, as it is in this case, then the wave function describing those two identical particles should change sign when we swap the two particles. So there are two aspects of this wave function. There's the spins of the particles and their spatial wave function. So if they're in a singlet spin configuration, swapping the particle spins gives a minus sign. That's antisymmetric. That's what we want. In the triplet case, swapping the particle spins gives no sign change. So that means that if we swap the position of the particles in space, the spatial wave function should be unchanged in the spin singlet case, but it should give us this minus sign that we need for antisymmetrization in the spin triplet case. And what that means is that if we've got two dark matter particles in a spin singlet state, their orbital angular momentum quantum number has to be an even number, because that's what gives you symmetry under exchange of the two particles in space. And similarly, in the triplet case, in the spin triplet case, if we've got two identical fermions, swapping particles should give a minus sign, which means the orbital angular momentum quantum number must be odd. So any kind of bound state that has a chi-naught component in it has to satisfy this criterion, which we can sum up as the angular momentum quantum number plus the spin quantum number should be even. Now, this doesn't happen for positronium bound states or for hydrogen atoms, because in that case, we're dealing with two totally non-identical fermions, and we don't care about the selection rule. But this tells us that we can only have dark matter bound states involving the dark matter at all where these certain properties are satisfied. Furthermore, we know, again, from quantum mechanics, that just radiating off a dipole photon, which is the dominant contribution to the capture rate in the positronium case, changes the orbital angular momentum of the configuration by plus or minus 1. The photon carries off some angular momentum, but it doesn't flip the spin. So what that means is that if I start out with an initial state, which is two dark matter particles coming towards each other, they're going to capture into a bound state. If that initial state is L plus S even, the bound state that we make will be L plus S odd. So it actually, that bound state can't have any dark matter, can't have any chi-naught component in it at all. So in fact, we see that there are, in this case, two kinds of bound states. There's the L plus S even bound states, which can be an admixture of chi-naught, and chi plus, chi minus. And there's the L plus S odd bound states, which have to be 100% charginos. They can't be made, they can't have any chi-naught component at all. So if we want to find these bound states, just as for hydrogen, we solve the Schrodinger equation. We're going to use quantum mechanical perturbation theory to work out the formation and transition rates. The distinction is in the hydrogen case, we had this potential that was just alpha over R. But now in this case, the potential is more complicated because it has to describe the interactions between all the two particle states. So in the example we just showed you, that's chi-naught, and chi plus, chi minus coupled by the gauge bosons. And what we've seen is that what kinds of states are available depends on the quantum number L plus S. So that in turn means that the form of the potential coupling the particles will depend on L plus S. In particular, if L plus S is odd, that potential can't allow any transitions to a chi-naught state because it's just forbidden by spin statistics. So what that means is that when we go to calculate the binding energies associated with the potential, the binding energies depend at an order 1 level on what L plus S is. Like for the hydrogen atom, it doesn't. There are only higher order corrections that depend on these quantum numbers. That you care about the principal quantum number, but not about the L or M for figuring out the energy at leading order. But that's different here. In these more complicated dark sectors, you will have multiple towers of bound states with different energy scalings depending on these quantum numbers. It's also true that the potential, if the potential is a matrix, you can think about like the characteristic energy scales associated with this potential as being obtained by diagonalizing the matrix, and the matrix can have multiple eigenvalues. So the generic behavior here is as soon as I have multiple force carriers, I'm going to have multiple towers of different kinds of bound states with different energies. So let me show you a concrete example of that in the WINO case. So this is a calculation that we did back in 2017. Well, we just split up the bound states that you have for the WINO in the spin singlets case and the spin triplet case. This scaling is just what would happen in the limit where the W and Z bosons are close to massless. And then on the right-hand side, we have the actual numerical calculations of the binding energies of the various states. But so you see, like this tower is not quite like the hydrogen atom. In the spin triplet case, the 1s state is actually degenerate with the 2p state. And we can show direct comparison to the hydrogen atom. This is what it would look like. This is what this tower would look like for the hydrogen atom case. This is what happens when you go to something like the WINO because of this L plus S dependent change in the energy, in the structure of the potential, and consequently in the energies of the resulting bound states. And so if we could see the transitions between the separate states, this would actually tell us a lot about the behavior of the dark matter and about what representation it's in, because this structure is very different in this kind of situation. Okay, so this also, this modifies things like which states are metastable. It modifies the energy gaps between states. We're used to thinking sort of like, oh, 2p decays promptly to 1s, 2s is metastable. Well, that is not necessarily the case here. Now, when we go to compute the formation rate, so now we also have selection rules in the formation rate. We know that if we're going to get to an even L state at the end of the day, we're going to need to have an odd L initial state, because we need to change the L by 1 when we radiate the photon. And that that initial state, if it's going to have 2 dark matter particles in the initial state, that means it has to be a spin triplet. So if you have you can have a bound state with L plus S even in your spectrum, but there is no way to get to it by single photon capture, by single photon dipole capture, starting from an initial state that has 2 dark matter particles in it, on the halo. So that's one thing, that there are novel selection rules that depend on the that depend on the spin quantum numbers of the state. The other thing that I wanted to tell you, and I'm just going to tell you this and not show you the derivation, but this goes to the question that was asked about the positronium formation rate, which is that we actually find we can, in the case where all the force carriers are massless, we can do this calculation analytically. It's again, just like the hydrogen atom in that case. And we find that the capture rate is suppressed by this exponential factor. So in the positronium case, this was e to the -4. It's really e to the -4n if n is the principal quantum number of the state. And then there's this additional ratio, which I've written as lambda I over lambda f here. Basically, this ratio is the ratio of the strength of the potential experienced by the incoming particles to the strength of the potential experienced in the bound state, which depends on whether the incoming state is L plus S odd or even. So this ratio for the positronium, this ratio was always just 1. Everything just fills the Coulomb potential. Nothing matters. It turns out that for the WINO, this ratio is 2 consistently. So what was e to the -4 in the positronium case becomes e to the -8 in the WINO case. For the quintuplet, there are 2 relevant eigenvalue combinations, and one is 6/5 and one is 3/5 for this ratio. So one of these you expect to be slightly more suppressed than the positronium. The other is actually less suppressed than the positronium. And so just from that estimate, which you can do just by looking at the potentials in the limit where the force carriers are massless, you can estimate roughly what this exponential suppression factor is going to be, but it varies in a highly non-trivial way between even different representations in the same gauge group, and between different groups in the dark sector will vary again. So the selection rules that I just talked about mean that these circled, so again, if we start out with 2 dark matter particles in our initial state, which we probably want because we probably don't have free charginos running around in the halo, then we only have a limited number of states which we can get into by a dipole, by unsuppressed single photon radiative capture. And in particular, what we find happens for the WINO is that at a 3 TeV mass, there's only 1 bound state in the spectrum, is this 1s ground state, and there is no way to get into it efficiently by radiating a single photon. It's there, but capture into it requires either a spin flip transition or a 2 photon transition, and those are both super suppressed. So for the thermal WINO, well, there's a bound state in the spectrum and it does nothing to a good approximation. These are some numerical results for the WINO. So just an update here. The original paper that we put out actually had a minus sign error between two terms in the capture rate. We'll be putting out an erratum soon. It doesn't change the qualitative answers. This was the plot in our original paper that showed the orange and yellow lines are direct annihilation, either to all species or just directly to a gamma ray photon line, which might be a nice signature to look for. And the blue line was the capture rate into the capture rate into various bound states for the WINO. And the baseline is that you can see that the blue line is a long way below the orange and yellow lines, at least at relatively low masses. This is in TeV on the x-axis. You can see that this doesn't even go down to 3 TeV. And the reason for that is what I just said, that at 3 TeV, there's 1 bound state and it is just super suppressed. You could say, okay, what if you have WINO-like dark matter that is a bit heavier? It's still true that the bound state formation rate is really small. In the updated version of the paper, once we fix the minus sign, the plot looks like this. So it's still so it doesn't qualitatively change things. The qualitative answer is that for the WINO, the bound state formation rate is almost always totally irrelevant. Okay, Now, the quintuplet, though, from these estimates that I just told you, you might expect the quintuplet to do better. So we have some work in progress on this. I will say that there are extra subtleties that I'm not talking about today about computing the annihilation signal for these heavy weakly interacting particles, because there are also large log terms in the standard calculation that you need to capture in the sum. That's been done in detail for the WINO. We have in progress work on it in the quintuplet. But one feature of our quintuplet calculation is that we're also doing the detailed calculation of bound states for that case. So here is what the result looks like for the quintuplet. The blue line is a direct annihilation cross-section, and the yellow line is the contribution to the corresponding cross-section through production followed by decay of bound states. And this gray line is where we think the thermal relic mass, the mass that gets you the correct relic density, is for the quintuplet. And so you can see that, well, depending on exactly where you are in this line, the bound state contribution could be it could be subdominant, or it could actually be quite significant. And the peaks in both of these are coming from resonant effects in the dark sector. Okay. So you can translate these questions into what do the limits from indirect detection look like on these scenarios on this WINO and quintuplet dark matter. Now, so one of the strongest constraints comes from looking for gamma rays from the galactic center direction with the Hess gamma ray telescope. And that can set pretty strong constraints on this signal. Now, such limits do come with a pretty significant uncertainty because we don't know how much dark matter there is towards the galactic center signal. But this upper panel is what things look like for the WINO forecast, which again has very little contribution from bound states. So this gray line is showing the forecast signal. The blue line shows the mass, of which we would expect the WINO to make up all the dark matter in the standard cosmology. The green line shows what the expected constraint is from Hess, and you can see that the gray line is well above this line down here, which suggests that it is ruled out. This assumes that the dark matter density continues to rise steeply and towards the galactic center. You can ask, all right, what if that doesn't happen? What if the dark matter density stops rising and flattens out within some distance of the center? You find that you need the dark matter density to be basically flat within about 2 kiloparsecs, or about 6,000 light years of the center, to avoid exclusion, which is a somewhat larger core than simulators tell me we expect in Milky Way scale galaxies. You can do the same exercise for the quintuplet, and you find that we might have sensitivity to this with current indirect detection probes. It's kind of on the borderline. For the quintuplet, if the dark matter density flattens out even within like a few hundred parsecs of the center, that would probably be enough that we haven't seen it yet. However, that's with current data. There's if we get the CTA, the Cherenkov telescope array, or other similar searches, we should be able to do much better than this. Okay, so this is all contributions to the annihilation signal. I told you that we know the bound states don't matter. I've given you some guidelines on how to estimate whether the bound states should matter or not, and told you for the quintuplet they do matter. We could also imagine looking for the emission lines from when the bound states are first produced. So so if we could see those lines, it would be awesome, because as I said, the differing energy levels depend very sensitively on what the representation of the dark matter is. If we could do dark matter spectroscopy, that would be amazing. The problem is that those lines are typically much lower energy than the annihilation signal, because the annihilation signal, you have the whole mass of the dark matter particles, whereas in these lines, you just have the binding energy. And because they're lower energy, the backgrounds tend to be higher and they're harder to see. But they could maybe act as a supplemental probe, where ground-based telescopes see your TeV scale annihilation signal, and space-based telescopes see the correlated GeV scale emission lines. For the WINO, it turns out that the rate for such transitions, as you might expect, because the bound state formation rate is super, super tiny, is just really low. So it doesn't look helpful. But this paper by another group back in 2017, which wasn't doing all the calculations we're doing for the quintuplet, but is probably a reasonable estimate, estimates that there is a gamma ray line coming from the transitions roughly 1 order of magnitude below the current sensitivity. So that's maybe not completely crazy, but you would expect to see the annihilation signal before you see the capture signal. Okay, so what would change if we wanted to do this for a more general dark signal? What lessons have we learned? Well, first, the mass scales can be really different. The argument that I just gave you about you want to be 3 TeV or heavier, that really relies on the weak coupling and the masses of the W and Z bosons. It would be hard to see the emission lines if what you're radiating is some dark force carrier and not actually a photon, right? Photons are the easiest things to see. Generic properties, we expect to see multiple different kinds of towers of bound states that can be displaced in energy from each other, which means that the rules for what states are metastable, what states can you capture into, do not follow your intuition from the hydrogen atom. And there's an exponential dependence of the capture rate on the group structure in dark sectors. So whether this is important or not can depend pretty sensitively on exactly what your model is. Okay. So that's what I wanted to say about indirect detection signals from these kinds of dark sector bound states. And I think I'm pretty close to the end of my time. So let me just talk briefly about the other example I wanted to bring up, which is that the bound states can also matter quite a lot for how the observed amount of dark matter is produced in the first place. Okay, so we'll go quickly through this example. So let me just say then first just what we usually think about for how the dark matter might be produced. Now, there are many, many scenarios for how the dark matter might be produced, and this is just one example. So suppose that if the dark matter could annihilate divisible particles, suppose that interaction was also active in the early universe. Then when the universe was sufficiently hot and sufficiently dense, the reverse process should also be allowed. You could have standard model particles annihilating into dark matter particles, just as might happen at freeze-out. And so in that case, we would produce a lot of dark matter in the early universe, just from standard model particles crashing together. But once the universe expanded and cooled and became sufficiently low in temperature that this dark matter production process was no longer efficient, the dark matter depletion process could still be efficient, and that would reduce the amount of dark matter into the universe. So this line in the right-hand plot is showing the amount of dark matter in a co-moving expanding volume of the universe. So in this phase 2, that abundance would fall exponentially. But eventually, it would become inefficient for two dark matter particles to find each other and annihilate in an expanding universe. And then we would end up with a fixed amount of dark matter per cosmological volume, which we call the relic density of dark matter, and we can compare that to the amount of dark matter density that we see today. So that leads to, so in this scenario, which again is not guaranteed, but is a standard and well-studied possibility, the amount of dark matter that we see today is determined by the strength of the annihilation. Now, but there's a limit on how far you can go with this. So you might say, okay, if I want less dark matter, I just dial up my annihilation cross-section to huge values. But there's a limit on how fast anything can annihilate, which is given by the unitarity bound. This is familiar from quantum mechanics. It's basically just saying the probability of annihilating in some measure can't be more than 1. So this gives you a mass-dependent upper limit on the cross-section for annihilation into anything. So in the form of that limit is in each partial wave that goes like 4 pi over k squared, where k is the momentum of the dark matter particles, and it scales linearly with the mass of the dark matter. So then that says, all right, if the dark matter is too heavy, the upper limit on this cross-section will be too small, and we will not be able to deplete enough of the dark matter in the early universe. We'll be left with too much dark matter early on, if it was ever in thermal equilibrium with the standard model. And so that gives us an upper bound on the dark matter mass of about 1 peta-electron volt for dark matter that was ever in equilibrium with the standard model under the standard cosmological history. So there's a loophole, which is that if you change the cosmological history, then this answer can change. And I'm just going to give you the sort of like very short version of this, because I know I'm at the end of my time. So the analogy that I want to think about here is strongly interacting dark sectors that are like QCD in the standard model. So the strong interaction of the standard model is confining. At low energies, the relevant degrees of freedom are things like protons and neutrons and blue balls and mesons, as opposed to quarks and gluons. If we go up to high energies, though, the relevant degrees of freedom are the quarks and gluons. And there's a transition between these two states when the quarks bind into their bound states, which is the QCD phase transition. Between the quark-gluon plasma and the deconfined phase and the bound states at late times. So you can ask what would happen. Now, we know that in the standard model, that phase transition is a pretty smooth crossover, but this doesn't need to happen in the dark sector. And there's lots of interesting studies about if there was a phase transition in the dark sector, what would the consequences of that be? But so you can think about this scenario. What if there is something like the standard model QCD sector in the dark sector? So the dark matter at late times would be the dark baryons, like the equivalent of dark protons, but at early times there would be a dark quark-gluon plasma. So what happens in this case? So we're going to posit here there are both dark quarks and antiquarks. the dark quarks and dark antiquarks can annihilate into dark gluons. And we're going to set up a mechanism that the dark, I wrote gluons, I really mean glue balls here, that the dark gluons, or the bound states of the dark gluons can decay into standard model particles. So if that's the case, the stable thing in the dark sector is the dark baryons, just like protons are stable in our sector. So now we have this modification of cosmology, which is the phase transition from free dark quarks and dark gluons into bound dark quarks and dark gluons. Does that change anything? So the answer is that it does. So if we posit, so let's posit here that, that the dark matter is heavy enough that first it undergoes this freeze-out process. We're left with some dark quarks in the late universe, and then a phase transition happens. Those dark quarks have to form into dark hadrons, and we want to know what happens in that process. So we're going to assume here that we have very heavy dark matter. So at the end of freeze out, it can't all annihilate away. We have too much dark matter left for the late universe. Then we go into the phase transition. So what we expect pretty generically is if the dark quarks are heavy enough, this phase transition will be first order. And so first order phase transitions proceed by making bubbles of the new phase, of the low temperature phase, which then expand. So what I'm going to show you, like, I'm going to flash a sequence of these little cartoons here, where the light blue means the dark quark-gluon plasma before the phase transition. The purple means the new phase of the universe, the low temperature phase, where you can only have bound states. And the little black dots correspond to dark quarks. So as we go through this phase transition, these bubbles of the new phase are going to grow. But the dark quarks can't get into these bubbles on their own. The only way they can get into the bubble is by finding other dark quarks to combine with to make bound states. And it turns out that what happens in this case is that the bubbles, the expanding bubbles of this new phase, push the dark quarks around. They herd them around and force them into the parts of the universe that are still in the original dark quark-gluon plasma phase. So as these bubbles continue to grow, eventually the situation that we'll end up with is that most of the universe is post-phase transition, but there are pockets left of the original dark quark-gluon plasma. And these have basically all the dark quarks in them because the dark quarks cannot get out of that phase. So it turns out that in that case, what happens is that as these pockets shrink, the dark quarks, well, so now as the pockets shrink, the density of the dark quarks and antiquarks goes up, which means that on one hand, their chances to form into bound states are much better. And once they form into a bound state, they can get out into the new low energy phase. But also their chances of just annihilating with each other are much higher. And so then it is a race between bound state formation and annihilation, and the process of bound state formation versus annihilation completely governs how much dark matter you have left in the late universe. So we call this mechanism squeeze out, because as the pocket shrinks down, essentially the dark bound states are produced and squeezed out of the pocket because it shrinks. So this is kind of like your if you're like squeezing an orange, the dark matter is like the juice being squeezed out of the orange. And so the amount of dark matter you have at late times just depends entirely on how much dark matter managed to form into bound states before it annihilated away. And we did the calculation in this case and find that this can make a 6 or 7 order of magnitude difference in how much dark matter is left in the universe. So the history in this case looks like this for the dark matter abundance. You go through the normal freeze out procedure where it falls off exponentially, then hits a plateau, then the phase transition occurs and it gets, and almost all that dark matter gets annihilated away. A remnant gets squeezed out of the shrinking pockets in the form of bound states. And that means that you can explain the observed amount of dark matter in the universe with much heavier dark matter, up to the PeV to EeV scale, above the usual sort of estimated limit, which is 100 TeV to PeV.
Tracy, really nice question.
Yeah.
Are you in danger of getting sort of late time old inflation here at the scale of the vacuum energy difference between pulse and true vacuum?
Yeah, so our it is a thing that you have to worry about like whether you can sort of get some period of effectively dark energy domination during this. Our phase transition is over pretty fast, and at the time when this is happening, the dark sector is a like the universe is very radiation dominated, and the energy stored in the dark matter in the dark sector components is small compared to the standard model. So sorry?
It's first order, but it happens fast.
Yeah, that's right. So in this case, it's probably not an issue, but in general phase transitions, absolutely. And I'll say one more thing and then I'll wrap up, which is I'm not going to go through the details of this specific model, but there's another way in which bound states matter here, which is after the phase transition, as well as these dark matter hadrons, we can also just have bound states of the dark gluons, so dark glue balls. In this scenario, they're actually the lightest particle in the dark sector. And if we don't want them to be the dark matter, we have to get rid of them somehow. So what we did in our model was we introduced a channel to the standard model so these things could decay. But we found that because, they're bound states, they have lots of different quantum numbers. There are some glue balls that are really hard to make decay. It's just really hard to write down operators that will make them decay, and they can generically have really long lifetimes. So in that case, while you don't get a period of early dark energy domination, you can get a period of matter domination with these glue balls, which are much more abundant than the dark matter, become temporarily the dark matter of the universe before they decay. And then when they decay, they inject a lot of heat into the standard model bath, and that further dilutes the dark matter abundance. So now this black line shows the resulting dark matter history. You have fall off, you have the phase transition, you have much less dark matter in the universe, and then when the glue ball bound states decay, they dilute the dark matter abundance again. And this means that drives you to even heavier dark matter masses, where dark matter masses up at the EeV scale and heavier are pretty fine. Okay. So I'll stop there since I know I'm over time. So the basic problem here is dark matter is more than 80% of the matter in the universe, and we don't know what it is. My talk has not solved that problem, sadly. But dark matter could potentially have complex structure that's similar to the standard model, and like the standard model particles, dark matter could form bound states. If that happens, then there could be significant consequences in a range of observational channels and for the history of the universe. If the dark sector has multiple force carriers, the generic features that we should expect are a modified tower of bound states and different decay processes and selection rules compared to their standard model counterparts. This could both enhance existing indirect searches for dark matter and open up new detection channels, especially if the dark matter is in a complex dark sector. And if we look at the case of strongly interacting dark sectors where there's a phase transition between the case where the bound states are important and where they're not, that phase transition and the subsequent decay of the bound states can really dramatically change the early history of the dark matter in the universe, and in particular allow for much heavier dark matter thermally connected to the standard model than you might have expected. So I'll stop there. Thanks very much.
Questions, and just a reminder to repeat your questions and I will answer.
So these quarks are way heavier, dark quarks are way heavier than the
Yeah, so in the
could they exist in the confined phase with a flux tube coming off of them, and then that would go hit another quark and then go inside the confined region?
Yeah, okay, good question. So the question was the dark quarks are much, much heavier than lambda. So could you have a situation where like a dark quark is just connected to another dark quark like the flux tube and have that combination end up inside the confined phase? Yeah, so it's a good question. The problem, so first, yes, the assumption that we made in this scenario was the dark quarks are sufficiently heavier than the confinement scale that the freeze out happens before the phase transition. If that's not true, if like the phase transition happens and then everything's still in thermal equilibrium after the phase transition and then freezes out, then it'll be more like the standard freeze out situation. The question about the flux tube, so the problem is that after the freeze out, the dark quarks are actually pretty rare, which is also why we get the first order phase transition. It's really just like a dark gluon plasma with the occasional dark quark sitting around there. That means because like they're pretty highly separated, it's hard to form a flux tube between them. We worked out, now you might say, okay, but if I try to push a dark quark into the confined phase, there'll be a ton of energy associated with that. So like maybe I can generate a new dark quark anti-quark pair out of the vacuum next to it and have a vacuum tube connecting those. We worked out the time scale for that to happen as opposed to the time scale for the dark quark to like just bounce off the bubble. And the bounce time scale is much, much, much shorter than the time scale for it to generate a new quark and quark pair, again, because they're really heavy. So it's really suppressed. So yeah, it's the fact that the freeze out happens beforehand means that the dark quarks are rare, they're outliers, and just the time scale for them to just bounce elastically off the bubble walls is much faster than anything else.
So we have a question in the chat. Show the cosmic history and how the abundance of the particles in dark matter decreases versus time, freeze out,
Yeah.
Any process that can be opposite, i.e. increases the abundance. I think about this, freeze out, drops the abundance by.
Yeah, good. So question is, can you have processes that regenerate dark matter at some point? I mean, the answer is I think the answer is yes in general, but like in the specific models that I talked about, it's probably, it's probably not significant. So I guess the problem with making more dark matter in general is the temperature of the universe is continually dropping. If you didn't have enough energy to make dark matter earlier, then waiting for the universe to expand more is probably not going to make the situation better. That said, there are scenarios where dark matter gets regenerated at some late time because like there was some heavy species that decayed away and made more dark matter particles. You can have situations where there's dark matter and also some heavier species in the same sector. And so like the dark matter can annihilate into that heavier species, but the reverse process is also valid. So I guess it's pretty common to get sort of like dark matter repopulation scenarios where there's something heavier than the dark matter. That energy is stored somewhere. It has, if the easiest place for it to go is into the dark matter, then as the universe expands, it will favor the movement of that energy to the lighter species. But yeah, in the scenarios that we have, that's not generally, that I've talked about here, that's not generally the case. But so yes, in general, dark matter repopulation mechanisms can happen. In this case, I think it doesn't. Yeah?
So sorry, if you probably addressed this, but could you say something about the lifetime of these bound states, like the WIMPonium states?
Oh, great, yeah. So the WIMPonium states, right? So we can ask what the lifetime is. If you're in the ground state and decaying, then it's parametrically just like an annihilation, but with an extra factor that depends on the wave function of the bound state. I actually asked my students this in a qualifying exam question a few years ago, but parametrically, this just gives you some extra powers of the Bohr radius. So it ends up parametrically scaling, I think, like alpha to the 5 times the mass of the dark matter. So for electroweak dark matter, you can put in alpha weak to the 5 times the mass of the dark matter for the decay rate. If the mass of the dark matter is 3 TeV, that is extremely fast on astrophysical timescales. So you make these states, they basically just immediately decay. But there's an interesting loophole to this. So that's from the ground state. So then, but if you can make the bound states at a much, if you can capture into significantly, if there are significantly higher and less bound states in the spectrum, and you can capture into them, and particularly if they have high angular momentum, so they have a high impact parameter. Classically, you can think of these bound states as like orbiting around each other at a large distance, and so it's actually very unlikely for them to collide with each other. The way to say that is that for the higher partial waves, you get additional powers of alpha in the decay rate, and they can actually be quite long-lived. So, in the annihilation rate. So the more likely process for those higher states is for them to decay down to lower states. But in a situation like the one we have here, where your towers are messed up and like you don't always have like a state at slightly lower L and slightly lower energy to decay down to, because again, the dominant transition is you emit a dipole photon and that changes L by 1. And that, so you have to like, but you don't split the spin. So you have to sort of stay on the spin singlet side of things. There may not be a state that is, below you and has delta L equals 1 that you can actually get into by the selection rules. And so you can get into a situation, at least in principle, in given dark sectors, where if you capture into slightly bound states, you could stay there for a long time. That's not something that I've had some discussions about this with other people. We haven't followed up on it in detail, but I mean, at least in principle, that could happen. You could end up in sort of a metastable high L state that lives for quite a long time. But once you get to the ground state, it's fast.
You were talking about direct detection signal, you were talking about detecting the particles that would make it.
Yeah, so if you were looking for like transition lines, you could look for those lines. But I mean, it is an interesting question, like could any of those be long-lived enough to actually like be stuck in the halo, be a halo population? Because if that's the case, the statements that I gave you about the direct detection signals being small assume that you just have chi-naught particles around. If you've got a bound state that has I haven't done the calculation, but if you have a bound state that has a significant chargino component, like it can just exchange gammas. It doesn't have to go through a loop of W's or anything. It can probably just do a tree level exchange of a Z and scatter off stuff. So it might be that even a pretty small population could have interesting direct detection signals. But I mean, the issue is that capturing into these high states is probably quite difficult. I said that there was that like e to the minus 4n times extra factors, where n is the principal quantum number of the state. So and you also may need pretty heavy dark matter or a pretty light force carrier to have states that high in the first place. They may just be unbound. So yeah, so I mean, I think that there's maybe an interesting calculation to do that, but I haven't done it.
final question in the room. There's one final question on the chat, which is
Yep.
just a request for you to comment a little bit on that early slide from Tim Tate. The diagram.
Yeah.
Just can you give some idea of how to think about any ordering element or criteria or how to
Yeah, so I guess there's a thing like, is there some ordering in like which of these should we think are more interesting, or which of these should we go after with experiments? It's a hard question. I mean, ways that people have used to order things on this slide are basically sort of like, let's order by how much we like the things in the black region, or how much we care about problems addressed in the black region. Like if you think that the strong CP problem is a really central problem and we need an explanation for it, and axions are the best explanation, then you may be driven to this axion corner of parameter space. I think, you know, when I was doing my PhD 15 years ago, lots of people were drawn to this part of parameter space because supersymmetry seemed like such an attractive idea. Since the LHE has not found weak scale supersymmetry, that, you know, that's caused a lot of movement away from this space. But so you can have sort of like your theory bias towards, is there something that I like in this outer region? Let me figure out what dark matter models could give me a result there. And I mean, I think like I have a little bit more prior weight on the QCD axion than on other possibilities, because it could potentially explain another problem. But I don't think there's any requirement that the universe has to be kind to us. Like, I mean, the strong CP problem and the dark matter problem may be independent. Like, I mean, Occam's razor is a powerful principle, but you know, so sometimes two things that look unrelated actually are unrelated to each other. So I mean, one thing that the community has moved more towards is basically just trying to search broadly and make sure that we don't have like obvious silly blind spots where we missed something that was very detectable because we were not theoretically prejudiced, because we just didn't look. And so one criterion is just to sort of ask, all right, can we do an experimental test that would efficiently probe a wide class of these models? If we do, then maybe we should do that, even if none of these models are particularly individually attractive. But I mean, it's a big question. Ideally, we would like, you know, I mean, I know many people on the particle theory side of things who are very worried by the fact that we don't really have a guiding theoretical principle that tells us where we should look for the next physics beyond the standard model. Naturalness was our candidate for that principle that says, all right, if you want to explain the mass of the Higgs boson, if you want to explain the hierarchy problem, then we should have new physics around the weak scale. But we've been searching for new physics around the weak scale with the LHC and with direct detection experiments for some time, and we haven't found something. Now, that doesn't mean you can't have new physics related to the weak scale. I mean, these WIMPonium examples that I gave you are like absolutely, you know, classic, just sort of new physics associated with the SU2 gauge group of the standard model. And as we said, they're not, well, okay, we know in the quintuplet may be marginally ruled out by indirect detection, but subsequent to some strong assumptions about what the dark matter density is doing towards the center, that could be the answer, but they probably don't solve the hierarchy problem. And so if you say, all right, maybe naturalness is not the correct guiding principle, then the question becomes, what is there? And there are people in my field who are thinking about this from the perspective of, okay, you know, we know that we need to get gravity into our theories at some point. From, you know, theories of quantum gravity, are there general statements that we can make about what the lower scale theories would have to look like that allow us to put some constraints on what the possibilities can be? But since we actually don't know what the theory of quantum gravity is, I mean, I think that's a very interesting program. It has not yet gotten to the point where it can say, right, you should think about strongly interacting hidden sectors at a GeV mass scale versus you should think about QCD axions versus you should think about models of the universe with extra dimensions. So yeah, no, I mean, I think the question of like how to order and prioritize these models is actually quite hard. And well, yeah, I mean, that's part of the reason that we have the SNOMAS process and then the P5 process. But yeah, I'd be very, very happy to get people's thoughts on that. But I mean, one sort of substitute for a theoretical guidance is try to make sure that we don't have blind spots and understand what kind of searches we can do to make sure that we're not missing something that is blindly obvious as soon as we look.
Excellent. Seems like a perfect note to end on. Thanks, Tracy, again.